Okay, our last talk is actually a late-breaking development that was submitted at the final hours when our abstract window submission was closing. So something exciting, late development for you. It's going to be presented by Stephen Fleming, who's one of our program committee chairman. Steve serves as the vice president for strategic business initiatives at the University of Arizona in Tucson, where he's focused on improving the university's engagement in the private sector. If you don't know it, Stephen is actually one of the founding figures in the new space revolution. So he was an investor in 10 aerospace companies and founded the Space Angels Network, which was pivotal in funding a lot of the early new space companies. So with that, we'll turn it over to Stephen.
Thank you. I don't mind a bit swapping places with Greg, but I will say when the program committee and Andrew made the schedule for today, we put Greg last so that people would stick around to see what he had to say. And now that he's gone, I'm kind of shocked people are still here. So thank you for staying. This is an unusual opportunity for me. This is, I think, my 5th Interstellar Symposium. And it's the first time I've been able to actually present something that's relevant to my day job. So this is my day job. This is the Center for Quantum Networks. It's headquartered at University of Arizona, Harvard, MIT, University of Massachusetts. You can read the logos there at the bottom, are all with us on this. If you're in the U.S., your tax dollars pay my salary, so thank you. And we are working on building very challenging quantum networks. And as I've told several people during the symposium, our position is the quantum computing problem is going to be solved about 6 different ways. It looks like that's well underway. Now it's a matter of engineering and scale. The challenge is going to be, if you have 1 quantum computer, that's interesting. If you have 2 quantum computers, that's maybe more interesting. If you have 3 quantum computers, you need a network. And most places who are building quantum computation are kind of hand-waving their way around, they'll hook them together. Our center is trying to hook them together. So in the process of building quantum networks, we're building quantum sensors. And one of the things that we have spent a good bit of time on in building quantum sensors is this area of super-resolution sensing, past the Rayleigh limit. And some of this is done as, where's Jeff sitting? As Jeff said, a lot of this is being done for reasons. I'll just say that a lot of this work was funded by Raytheon, and you can go figure out the rest of it. But what I want to talk about is the overlap of what we're doing with super-resolution sensing and potential detection and eventual potential imaging of exoplanets from, at least potentially, from Earth's surface. So when we're talking about telescopes, size matters. This is underneath the football stadium at University of Arizona. This is the Mirror Lab. How many people were in Tucson 2 years ago? Because we ran tours of the Mirror Lab. The symposium was in Tucson 2 years ago. We are building these mirrors. I'll jump ahead and come back. This is what we're building, is the Giant Magellan Telescope in the Atacama Desert. There's 7 of these mirrors, each of which is that big, 8.5 meters across. And the point of that is to build great big buckets to capture lots of light. And there's lots of different reasons of doing that, but for the stuff that we care about, if you're thinking of an exoplanet, think of, whatever random star the exoplanet is orbiting, a photon leaving that star, bouncing off the atmosphere of that star, and then managing 1 over r squared to bounce directly into your bucket sitting here on Earth. There's just not that many photons that are going to be lined up to do that. And so you need as big a bucket as possible to be able to capture those. And so the Giant Magellan Telescope here is under this very straightforward assumption of, just build bigger pieces of glass and hook them together, and you'll catch more photons, which is true, and that's why we're doing this. And that's why when you put 7 of these together on a mountaintop in Chile, it's $1 billion. That's what that thing costs. And they've raised the money, and it's well underway. And I mean, the 3 of them are in place already. And the one, I think that's actually a photograph of number 5, but we're building number 6 right now, and we'll build number 7. It takes about 3 years to build one of these things. It's a complex endeavor, and what I'm hoping to propose for your consideration is there may be simpler ways of doing similar things for certain applications. I will take a detour and note that's an 8.5 meter diameter mirror. The fairing of Starship is 9 meters. Think about that. It would be nice to just wrap one of these in styrofoam and launch it and build a telescope structure around it on orbit. That would be kind of cool. But what we're fighting is the Rayleigh limit. The rocket business that Jeff Grayson got me into a long time ago talks about the tyranny of the rocket equation. I was amused that Victor Toth I think it was Monday, I've lost track of time this week. Victor Toth talked about the tyranny of the diffraction limit, which is the same sort of thing. It's just like, damn it, physics doesn't do what we want it to do. And so when you have 2-point sources focused through any sort of lens system, whether it's a converging lens or a mirror system or whatever, you wind up getting the 2-point sources close enough together that you simply cannot distinguish between them, and at that point you can't get useful information out of that image. Or so we thought. Maybe that's not necessarily true. Here's the math. I think Victor had the same equation. And if you're looking at doing, something at extrasolar distances, the more precise the resolution it is, the bigger the aperture of the telescope that you're building needs to be. And if you're trying to get a 40 by 40 image of a planet orbiting Alpha Centauri, you need a telescope, a couple of kilometers in diameter. I think Victor was talking about even higher, or he was talking about even higher resolution. I think he was talking about 10 light years. It was an even bigger number as a telescope, the size of the Earth. It doesn't matter. We're not going to build one that big. There's other ways of doing it. But just again, this one that cost $1 billion is, what does it say, a 25,000th? It's some silly fraction of the size of a light bucket you would have to build to do this sort of imaging at extrasolar distances. But we're doing lots of interesting work with quantum sensors and quantum information science, and it may be that using quantum technologies, you can actually beat the Rayleigh limit, and you can actually use all of the phase and amplitude information in the collected light and extract that in ways where you can actually distinguish between point sources that are closer than the Rayleigh limit. And this is what we're calling superresolution. And if you just Google that word, there's lots of work going on, even in the open literature, on superresolution imaging. Not a lot of people are currently doing it for astronomy, but I think that is something that maybe this community can help encourage, is to use these technologies for exoplanets. The idea is simple. We've seen multiple aperture telescopes before. Instead of having one 3-meter mirror, you could have 3 1.5-ish, 1.7 meter mirrors scattered over, some fraction of an acre. Mirror costs go up more than exponentially. So 3 1.7 meter mirrors are a lot cheaper than one 3-meter mirror. And you can actually, start thinking of ways, well, maybe we don't use 3, maybe we use 7, maybe we use 18. You can start scaling these arrays in interesting ways, and trying to use lots of small mirrors to do things that you simply can't build one big mirror big enough to do. So this is, again, physics hates us. So this is the way light focuses, which is imperfect. Probably doesn't show that well on that screen, but there's kind of colored fringes around that dot of the airy disk. And this is just the diffraction of light. This is the way light works. And this can be described as the point spread function of any optical system, is how tightly can you focus this. This is the top left, is the one big-ish mirror, 3-meter mirror. The bottom left is 3 smaller mirrors, 1.5 meters. The scales are not the same, so this is scattered over, a 20-meter square, so the size of a suburban yard. And if you look at the point spread functions of those, the one on the top right is pretty predictable. It's one big round mirror, you get one big round point spread function. You can start getting interesting effects when you start using multiple mirrors, is the point spread function literally spreads out across that entire 20 by 20 meter area, and you can start detecting things that you really can't do with what's up there in the top right. So, for example, with resolving an exoplanet, I mean, the first thing you need to do, we eventually want to talk about imaging, but first you just want to know if there's one there or not, is you just test the hypothesis. Okay, there's the star. Is there something else, in the very close field of view of that star which might qualify as an exoplanet? And, is that present or not? And can you tell that with either of these optical imaging systems? The top half of this is what we normally think of for modern day telescopes, is you have whatever's out there, you go through an imaging system, and then you come to an image plane, which these days is a bunch of digital detectors, and you simply measure, what does the image look like? This is actually no different than the digital camera inside your cell phone. What starts getting interesting is if you start treating the quantum modes of light in these fibers as things you can extract and process separately. And so this is something called B-spade binary. I spelled it out somewhere. Binary, it's on the next slide. Spatial, whatever. We'll spell it out in a second. But the idea is using evanescent mode coupling, and that probably actually involves curving the fiber around a mandrel or something. This is a schematic. You can actually extract the central mode of light being carried through this fiber and physically separate it to send it to different detectors than the rest of the modes, and the rest of the modes will preferentially contain the off-axis light in the image, whereas the central mode will preferentially contain the on-axis light. It's not perfect, but there's a ratio there where you can actually, and this is the point of super resolution. This is actually where you can extract information from the center and from the outsides of the field and separate them to different detectors. Yeah, here, binary spatial mode demultiplexing. I knew this was spelled out here someplace. So the idea here in our system, if you had an exoplanet, that's the off-axis. It's all combined going to detector. The B-spade system will physically split these up. So the starlight goes up. That's the fundamental point source function. And the other stuff, which we hope has an exoplanet in it, goes to this other detector down at the bottom, and you can process those separately. So what we've basically built by doing this quantum coupling, you've built a nuller for the starlight without doing some exotic sun shield that has to be aligned to ridiculous levels of precision. You're turning down the central image and turning up everything around it, which we hope includes exoplanets. And you're doing all this, on a tabletop. You're not doing this with, star shades that are sitting out, tens of thousands of kilometers, which is kind of cool. And then we haven't built one of these yet, but if we run the simulation, if again you go back to this hypothesis of, is there an exoplanet in this image? And we run the simulation using, this is called ring 3. This was the 3 smaller mirrors. The error rate is substantially better, like a lot better than just using one big mirror. So what you're seeing is with a relatively limited number of photons, and again, back to 1 over r squared coming from Alpha Centauri, with a relatively limited number of photons to work with, you can make that determination much more quickly and much more accurately that, yes, there's an exoplanet there, or no, there's not an exoplanet there. Let's move on to the next target. So it substantially increases your ability to scan these stars and figure out what else is in that image. Later on, that's a 40 by 40 pixel image of the Earth. That's harder. I don't think it's unreasonable to do this from Earth-based systems. If you start building these things on orbit, it gets easier, but then there's other engineering issues with doing that. But it looks like 100x increase by using these techniques is reasonable. And 100x increases in anything get my attention, because that's when you can start really doing things differently. So using these binary spades as a nuller for starlight for terrestrial-based systems, I think will greatly enhance our ability to detect exoplanet candidates, and eventually with a lot of good hard engineering work, I hope we can get to imaging exoplanets without having to go there first, because we want to know where we go before we go there. I will confess this is not my work. This is the work of some of the people that I work with. And when I said I was going to a conference on interstellar and I'd love to talk about exoplanet imaging, they said, "Oh, we can do that. You get to present it." So I have now presented someone else's work. I can answer a lot of questions, but a lot of them I'm going to go ba-ba. So with that, I'll answer questions until Andrew gives me the hook. Thank you. All these files are online, and I live on Twitter, so you can find me there. And if we can run a mic, here too. Robert's here in the front.
Hey, do you still have access to the spectrum with this to look at?
Oh, yeah, absolutely, yeah. Yeah, you can do spectroscopy. You can do anything you want with it, sure. Yeah. Okay. Yeah. Yeah, it's just photons. So yeah, absolutely. More questions? I'm between everybody and box lunches and tours and things, and I realize that. So I'm not offended if there's not a lot of questions. Oops. What?
Thank you for that.
They're both in blue. We learned last night those are different blues. If you speak Russian. Sorry, go ahead. So,
I wanted to ask, earlier you were talking about how you might be able to analyze the light and pick things out like polarization and stuff like that.
Mhm.
What extra data could you get from the polarization of light in this scenario?
way beyond my level of knowledge. Don't know. I can ask, but at that point, I probably need to not only work with my people, but the people across the street who are in Stewart Observatory, who are the actual astronomers. And so, hopefully the 2025 version of this, we have an astronomer author, and we've done some of that work. So yeah, that's right in front of you.
So I just wanted to understand a little bit about what, when people talk about beating the diffraction limit, it gets my attention.
Yep. Because I was told you couldn't. So that's how I grew up.
Well, but the diffraction limit really represents a boundary at which you have an exponential decay of the recoverable wave vectors, right? So the wave vector basically is the inverse of the spatial resolution at which you can recover something. So then it's also so it's a statement that below the diffraction limit where you have cutoff, you have an exponential decay of the recoverable information. So I think, isn't it the case that what you're doing here is that you're essentially blocking the stellar radiation, you're making the light from scattered light from the planet more recoverable? Is that a way of
yeah, you're not blocking it as much as you're kind of, if you had a potentiometer, you're turning it down. You're
aperturing it.
Yes. So so you're emphasizing the external modes more. And so there's always a Rayleigh limit, but by using different modes, you're examining the Rayleigh limit for a different subset of the photons that are coming in.
Yeah.
So,
okay.
I think 2 seats behind you. These are all the questions are lined up here.
Some over there too, but just want to point out the Rayleigh limit is just where the maximum of one overlaps with the minimum of the other for say a circular aperture.
Right.
So we violate the Rayleigh limit in communications theory all the time. Everything you're doing right now, for example, that's streaming out, is beyond the Rayleigh limit, because it's nothing more than saying the Rayleigh limit is when the signal to noise is unity. When the signal to noise is not unity, then it's easily, it's a false understanding of what a Rayleigh limit is in terms of limiting the ability to resolve. That being said, the reason that the comment that, multiple apertures are better than one aperture is because you are throwing away all the phase information when you converge onto a detector, and you're only using the amplitude information, not the phase. You don't need a mirror or a conventional imaging device at all if you have the amplitude and phase information. So for example, in a lensless camera, you can do interferometry between all the pixels, which is how a standard interferometer works. As long as you have the amplitude and phase information, you just have to be able to detect amplitude and phase. So this is, I think, one of the misconceptions in imaging in general. You don't need mirrors, you don't need conventional optics if you have the ability to measure amplitude and phase.
I'll pass that on. Appreciate it. I think there's one over here. Wait, against the wall. Okay.
Not so much a question, but as a thank you for pointing out one thing which I didn't hear throughout the week here. And everyone's been using Alpha Centauri for possible targets for missions because they're possible. But you made a statement, and thank you, and that is, you want to see where we're going before we leave. And I think that was a brilliant statement, because I don't know about you, but I like to know where I'm going also. And so thank you for that. I think that's one of the things we should think about a little more, perhaps, for future discussions.
Yeah, there's a lot of characterizations going to have to be done before we spend a large number of dollars to go someplace. We need to have a good characterization of it. Was that it, or okay?
That's it. Yeah,
Thanks.
let's thank Stephen.